Introduction to Acids and Bases, lecture number 22. So we're going to continue our discussion on these equilibriums and now relate these to specific types of equilibriums in terms of the acids and bases. So let's review from 111 our definitions. We had two definitions of acids and bases from earlier. The first was the Arrhenius definition. An Arrhenius acid is something that produces H plus or H3O plus in water. And so we take this acid, put it in water, we get H3O plus or H plus. An Arrhenius base is a substance that produces OH minus in water. So we take the base, put it in water, we get OH out. So this is a very specific definition. Remember, we're taking that substance and seeing how it reacts in water. To make a more general definition, remember we have this Bronsted-Lowry definition, or Bronsted definition of an acid and a base. A Bronsted acid is a proton donor, so we're transferring this proton, this H plus, from one species to another. We call that an acid. A base is something that accepts that proton. Right? So this is a more general definition. So all those Arrhenius acids and bases that we talked about are still going to follow this definition. But not all of the Bronsted-Lowry acids and bases will satisfy the Arrhenius definition, because they don't. This takes that necessity of water out of the equation. Right? So now that we remember what an acid and base are, remember back we said that there could be two types of acids or bases depending on whether they were strong or weak electrolytes. So we can have a strong acid versus a strong or weak acid. So remember, a strong acid is something that completely dissociates into ions. So we take something like HCl. When we put it in water, we get H pluses and Cl minus. Completely dissociates. Right? So when we look at the solution, there are no HA molecules. HA is our sort of general definition of an acid. There's no, in HCl, even in a dilute solution, there's no HCl. They exist only as H plus and Cl minus, because it's a strong electrolyte. Conversely, if we talk about a weak electrolyte, that's something that only dissociates incompletely, or less than 100%. So when it's in water, there is some of that original molecule present. So if we look at a weak acid like HF, in all situations we have some molecules that exist as HF in addition to the H plus ion and the F minus ion. Right? There's always some of these values. Right? One way we can, because they're weak electrolytes, the easiest way we can see that is looking at the equilibrium constants. A strong acid means it completely associates completely. This K value is going to be very, very large. Right? So large, in fact, there's none of that reactants left. Where our weak acids are going to have some K value. Right? It's going to be a smaller number less than 1, typically, because there's very little bit of that ions are produced. Most of it stays as the individual molecule. Right? So that K value is going to be less than 1. So with a small K value, we call those weak acids. So we can then define this acid, this K value, instead of talking about a Kc or a Kp, we can say that this is the dissociation equilibrium expression for an acid. We're going to call it Ka. So if we look at this general expression, Ha, this some acid, plus water, is in equilibrium with H3O plus and A minus, we can define the equilibrium expression as the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. Right? So our equilibrium, then we can say that Kc is really equal to Ka. It's more specific. This is an equilibrium expression for an acid. Right? Therefore, the larger the value for this Ka, the stronger that acid is going to be. The smaller the value it is, the more negative that exponent, the weaker acid is going to be. So there's a direct relationship between the size of Ka and the strength of this acid. So here in this table we can see some general Ka values. We look at things like acetic acid, which is in vinegar, has a K value of 1.8 times 10 to the minus 5. Hydrofluoric acid, HF, has a Ka value of 6.8 times 10 to the minus 4th. So we can see all of these, because they have fairly small K values, are all considered weak acids. So aside from memorizing a list of strong acids or strong bases, there's a couple rules to help us remember these. Strong acids are always going to include those hydrohalonic acids, HCl, HBr, HI, right? Not HF, because of the high electronegativity of fluorine, but the rest of them, HCl, Br, I, are all going to be strong acids. For the oxo acids, excuse me, we're going to say it's going to be a strong acid if the number of oxygens in that polyatomic ion exceeds the number of hydrogens, ionizable protons, by 2 or more. So if we look at nitric acid, for example, HNO3, we have 1 ionizable proton, or 1 hydrogen, and 3 oxygens. So that exceeds by 2, so we would predict, and it is true, that nitric acid is a strong acid. Right? So then weak acids are going to include things like HF. HF is the only one of those halogen acids that is weak. Or things that have the hydrogen bound to something that's not a halogen. So for example, HCN, cyanic acid. The hydrogen is bound to the carbon, not a halogen, not an oxygen, so it has to be a weak acid. Or those oxo acids that contain a number of oxygens less than the rule above. So 1 is equal to or exceeds by 1 the number of hydrogens. So like HClO, we have 1 oxygen, 1 hydrogen, that is going to be a weak acid. And then this group of organic compounds, which we call carboxylic acid, which have the general formula, as you can see here, this R, some group of atoms, COOH. So we have if we look at think of the Lewis structure, one of those oxygen is double bound to the carbon. We have a single bond between the carbon, the oxygen, and the hydrogen. So these are the general form carboxylic acids. Those are also going to be weak acids. We can set another set of rules for the bases. Right? Strong bases include those water-soluble compounds that have either the O2 minus or the HOH minus, the hydroxyl ions. And that cations are usually the most reactive metals. So the alkali metals, the sodium, lithium, potassium, rubidium, cesium, all of those hydroxides or oxides are going to be strong acids. And then the soluble forms of the hydroxides for the alkali earth metals, those group 2 metals, calcium, strontium, and barium. Those are, from our solubility rules, if you remember, are the soluble ones, so they are going to be strong acids. Weak acids then include everything else. In general, we can talk about ammonium, NH3, as being a weak acid, or those amines, again, these organic compounds where we are derivatives of this ammonia, if you will, where we replaced at least one of those hydrogens with carbon. We can replace all 3 of them with carbons to make this tertiary amine. These are all going to be weak acids because of the lone pair present on the nitrogen. So if you memorize the classifications for the strong acids and strong bases, then anything else that doesn't follow those rules has to be weak. That's my suggestion. So if we look at our definition of an acid or a base, right, knowing the fact that water is a combination of in H and OH, then we can define water as both being an acid and a base. So we can have what we call the auto-ionization of water, where one of those waters can react or accept a hydrogen from another water, water can donate its hydrogen to another one to form H3O plus and the OH minus. So it's acting as an acid, acting a base. So water then is an acid and a base. So we can write then an equilibrium expression for this equilibrium reaction, right? So we can take this H2O is in equilibrium with H plus and OH minus. So our K value would be the concentration of the H plus times the concentration of the OH minus. Right? So this is the equilibrium expression for water, so we call this value Kw. Right? And Kw is going to be a certain value when we have an equal concentration of H plus and OH minus. At 25 degrees, Kw has a value of 1 times 10 to the minus 14th. Right? So the normal in water at 25 degrees Celsius, we would then have a concentration of H plus and OH minus of 1 times 10 to the minus 7th. Right? So if those two are equal, we call this a neutral solution. Right? If we have more H pluses than OH minuses, right, then we do under when it's just pure water, we call that an acidic solution. If we have less H pluses than OH minus, we call that a basic solution. Right? Now, all of this is in terms of this concentration, this K value, or the concentration that exists there of 1 times 10 to the minus 7th. Right? So it's hard to talk about concentrations that are that small when we're talking about the exponents and changes there. Right? So we've come up with a shorthand notation for distinguishing these fairly large changes in concentration. And that you all are aware of is the pH scale. And we define the pH, this P is a mathematical designation, so the P of the H, so we're taking the negative log, is what the P stands for, of the H plus concentration. Right? So then, if the H plus concentration is equal to the OH minus concentration, which I said at 25 degrees was 1 times 10 to the minus 7th, the negative log of that concentration gives us this magical value of pH of 7. Right? Then if we have higher concentrations of H plus, where the value is greater than 1 times 10 to the minus 7th, if you take the negative log of those values, you find numbers that are less than 7, the acidic conditions that we're familiar with. Conversely, if we have less H plus than OH minus, or numbers, the concentration of H plus is less than 1 times 10 to the minus 7th, take the negative log of those values, you're going to get a number that's greater than 7. Again, we call those basic conditions. And in general, you remember that as the pH goes up, the amount of H plus goes down. Right? So if we now know the equilibrium value, the Ka, then we can denote, so if it's an acid, the conjugate, remember those terms, so we take an acid and it reacts with a base to form a conjugate acid and a conjugate base. We can then convert the strength of those two things using this Kw. And we'll talk more about that later. The conjugate base of so if we talk about these relationships, the conjugate base of a strong acid is going to have no acid ability, right? You're not going to be a strong acid at all. And we have this process we call leveling. So the H3O plus is the strongest acid that we can have in an aqueous solution, and OH minus is the strongest base we can have in an aqueous solution. All these strong acids, strong base are leveled, or the same amount, because they're forming these two substances in water.